I assume all of you are somewhat familiar with LLMs by now. They're pretty cool. Under the hood, they're doing lots of calculations. Just to give some sense of scale, this 2 billion parameter model does, with some napkin math, 4 billion floating point operations per token. If you're generating a few paragraphs of text, it's reasonable that this model could be doing closer to 1 trillion floating point operations. And this is for a very tiny model. Some of the smartest models today could be doing many, many times that, and they have an insane number of users using their websites. And yet, when I talk to one of them, they write faster than I can read. What's going on here? One of the biggest things ever to happen to machine learning was GPUs. This is why NVIDIA is worth so much right now. And to see why, we're gonna have to see what makes a GPU fast. Originally, they were meant for gaming. When running a game, the engine has to turn the absolute 3D point vertices of the game environment, which don't change no matter where the player is, into the correct positions relative to where your player is. Video games have thousands of these 3D points, so you run into a small problem. A CPU would go through point 1, then point 2, and then on for all of the 1,000 points, which is sequential and slow. GPUs offer much, much higher parallelism. I actually want to use some math notation here, just to really show what's going on. You have this 3D vector representing a 3D coordinate of the game. This is a global coordinate that then has to be turned into the space relative to where you are. So you can apply this 3x3 matrix, which is a transformation from a vector in 3D to another vector in 3D, which turns this point into where it is relative to you. I'm not going to go too deep into the details of the entries of this matrix, but what's important is that to compute this output vector, you do many independent operations. So you take this row to get this entry, this row to get this one, and this row to get this final one. And the 3 outputs of the final vector don't depend on each other computationally. So this is one way in which you could potentially see why a CPU going from row 1 to row 2 to row 3 would be slow. There's in fact an even bigger speedup. You can combine every single 3D vertex in the game into a matrix that becomes 3 by n, where n is the number of vertices in your game. Then, this 3x3 matrix multiplied by the 3 by n matrix gives the entire 3 by n shifted output coordinates. And again, each vertex's operations, if you want to trace it, are totally independent from one another. This combination of independent entries into a new dimension for more parallelization in machine learning is called batching. And the way GPUs speed things up over CPUs is they can parallelize simple operations by orders of magnitude. And with this example of matrix multiplies, what is a transformer but a bunch of matrix multiplications? Sure, there's a few nonlinearities in there, but the bulk of the operations done inside a transformer are matrix multiplies. So GPUs are a huge speed up over CPUs here. And there's another interesting property of transformers too. I assume you have some familiarity, but just for a quick recap, a text prompt is split into tokens, which correspond to the super high dimensional vectors that the model has learned. These, in turn, pass through attention layers and MLP layers, which will become important later. You can think of the attention layers as tokens communicating with one another, but information never passes backwards. This is because if tokens were allowed to look at future tokens, this would kind of give away the answer of predicting what comes after them. To make this a bit more concrete, if you give a model the prompt of "the cat sat on," from the perspective of the token cat, literally nothing exists after it. It's the same as if you passed in just the cat. And in fact, you can verify this. You can see for yourself that the probability distributions at token position 2 are the same, whether I'm passing in the cat or the cat sat on. Basically, in the mind of token 2, the only tokens that exist are token 1 and token 2. And for token 3, it never sees token 4. So it ends up being that every token position in the final output gives its own probability distribution for its own prediction of the next token, even if it's not the last token. If you do know a bit more about how attention works, you know there's key, query, and value vectors produced by every single token at every single attention head. Due to this masking property, the keys and values for token 2, for example, never depend on anything after it. This seems unimportant, but it's actually the cause of a huge speedup. Think about what happens when this new the token is predicted here. This token is appended to the sequence, so the new prompt is the cat sat on the, and the LLM has to predict what comes next. It creates a query vector, and the dot product of this vector is taken with all of the preceding key vectors. But wait, those key vectors are the same as the last step, because again, the token on doesn't know that the was just added. So the keys and the value vectors never change as you auto-regressively add more tokens. These constant k and v vectors can be stored, and this is referred to as the kv cache. This is actually a huge speedup, especially at longer contexts. Without any kv cache, you'd be doing insane amounts of repeated work. To use some technical terminology, kv caching brings the time complexity of attention down from O of n squared to O of n per step. There is, however, no free lunch here. The drawback to kv caching is that you're storing an insane amount of extra vectors in memory for the speedup. You can even calculate how much. For a given context length, you're storing 2 vectors, each of dimension d. So you have to store this for every single layer in order to avoid recomputing them at all. So the formula becomes 2 times L times D times the context length times how many bytes you take per float. This scales as the sequence length increases, and for long context lengths with high precision and many layers, the KV cache for a large model can take gigabytes of VRAM. So you're trading off time for memory here. But if you notice, in the beginning when you start a chat, there's no history of your previous tokens, so there are no KV vectors to cache. This initial stage of inference is called Prefill. Since this stage has many input tokens already given to it, it'll process all of those tokens in parallel, build up the KV cache for all of them, and then predict the first token. The next stage, when it starts making the new output tokens one by one, is called decode. In the decode stage, it already has the KV cache of the previous tokens it can use, and it's doing one token at a time instead of many. Let's start with prefill. Prefill involves taking all of the input tokens at once, and thus the matrix multiplies are extremely large because you have to do it for all n tokens. So we're doing a lot more operations than we would be if we were processing a single token. This means that the compute is more of a bottleneck than the memory bandwidth, as we transport this one huge matrix along with the model weights from the memory to the core one time, and then we do a large amount of computation on this chunk of memory. The ratio of how much work you're doing for every number you move into your cores is referred to as arithmetic intensity, and prefill has a high arithmetic intensity. Decode, on the other hand, is memory bound. Not only are you doing one token at a time, which lowers your arithmetic intensity and means you have less computational operations to perform, you also have to fetch the KV cache for every preceding token and the model weights, which requires memory bandwidth. So for a single token, you're reloading all of the model weights and all of the KV cache. So you can imagine the vast majority of the time here is spent shuttling tensors in and out of the compute cores. You kind of want to be compute bound rather than memory bound, because that means your hardware is doing what you paid for, rather than the cores just waiting to be fed numbers all the time. So how can you reduce how memory bound decode is? One simple idea is what we talked about in the beginning with the GPUs and the gaming. You can batch multiple user inputs into a new dimension, embed the entire batch set of prompts, and pass the entire batch set of embeddings into the model. By the way, a higher dimensional form of a matrix like this 3D matrix, is referred to as a tensor. Since each user's input is independent, they can be handled in parallel really effectively. now you're doing a lot more computation on each individual tensor, and you're spreading the cost of loading the model weights across multiple different prompts, because all the prompts share the same model weights. What cannot be amortized though is the KV cache, because each individual chat has its own KV cache. This makes the KV cache a huge bottleneck. It's basically like the biggest bottleneck at long context lengths. The KV cache formula we showed before with batching has this extra batch size term. So this massive cache is taking the bulk of your time to transport while your compute cores are just starving to do the next multiply. There's thus been a lot of work at mitigating this bottleneck. There are optimization techniques such as grouped query attention, which means small groups of attention heads share the same key and value matrices. And going even further, multi-query attention, which means all the attention heads in a single layer share the same key and value matrices. And there's a lot more work being done right now on KV cache compression with cool methods by DeepSeek and Google and way more. So these were the attention layers, but I also want to give a bit of love to the MLPs. If attention is the communication layer, MLPs are kind of the introspection layer, where a token can think about what it just learned. And again, each token does this independently, so it can be represented as a single matrix multiply, then a nonlinearity, which I'm just going to totally ignore, and then one more matrix multiply. At the frontier, you want your model to be as smart as possible, while being as fast and cheap to run as possible. So one way you could do this is by splitting up your layers. So for example, say your MLP layer has 10 billion parameters. Instead of requiring you to do a matrix multiplication with all 10 billion parameters, you can split this into say 5 experts, each with 2 billion parameters, and then training a very small routing layer that chooses 2 of these experts. The tokens are then only passed through these 2 experts, which means you magically reduce your active parameters down to 4 billion, but keep your intelligence much higher than a 4 billion parameter model. Now I want to go back to the KV cache formula we saw earlier. I kind of glossed over this bytes per float parameter, but this is actually tunable, it's not a constant. So if you were clever enough to think of this, you might be asking yourself why we don't reduce this. And this isn't just true of the KV cache. You could reduce the size of your model weights, and the internal activations of your forward pass, and basically everything. And if you were clever enough to think of this, you've basically reinvented quantization. So the way floating point numbers are represented in computers, they have 3 types of bits. Sign bits, which I'm going to mostly ignore, exponent, which I'm going to call range bits, and mantissa, which I'm going to call precision bits. This is the official standard for FP32, which is a pretty common training format. This is a bit complicated, but the gist is that your range determines how large or small your values can get. So increasing that means you could reach much higher maximum values than before, say like 1,000 instead of 200. The precision bits specify how many values in between each given power of 2 you can represent. So say instead of being able to represent only 10 numbers between 2 and 8, you can represent 20. Typically, in most ML floating point representations, the precision bits are compressed more than this. For example, in bfloat 16, which is another very commonly used data type, the precision bits are cut from 23 down to 7. All of the 16 bits that are cut are precision bits. Because as it turns out, and this is something people have discovered, is that neural networks are very robust to reduce precision. So even though you lose a little bit of performance, it's really not as much as you'd assume. There are many formats which compress the range too, but typically the precision is compressed more. And there's been research on compressing very, very, very far down, with even things like 4-bit becoming more common, and some research going all the way down to 2 or even 1 bit. At smaller formats, like 4 bits, the precision or range bits stop having clear demarcations. They use like some very clever tricks. But going down from, say, 16 bits to 4 bits means you can transfer and do computation multiple times faster per second than you could before. I want to go through one more non-hardware optimization that you can make for a speedup. And it's a cool idea that builds upon the fact we mentioned before, that models can predict the next token probability distributions for every token in the sequence in parallel. So imagine you have two models, one larger model whose inference you want to speed up, and imagine training some small model that's small enough in comparison that forward passes on this model are basically free in comparison to the big model. Let's say your prompt is the quick brown fox, and we want to predict jumps over the lazy dog. This is 5 tokens, so if we did this entirely with the large model, it would take 5 passes of the large model, which is insanely slow. So in comparison, you can run 5 passes of the smaller model on this prompt, which is much faster. So let's say the model ended up generating jumps over the black cat. So now we exploit the fact that our model can output probability distributions in parallel. So we pass in all of these generated tokens, the entire sequence, into the larger model to verify that our small model was not being stupid. So probably what will happen is the large model will verify that jumps over and the were valid and decides that the rest weren't. The core idea is basically that verifying n tokens is closer to the same amount of time as generating a single token for the large model, and generation is much cheaper if you use a smaller model. But how do you decide what's valid and what isn't? Well, here's one way you could do it. Say the probability that a large model gives to a token is p of x, and the probability the small model gives to a token is q of x. You can accept the token with the probability p of x over q of x clamped down to 100%. And the first time you end up not sampling this, the first time you end up rejecting, you can sample from this corrected distribution. It's worth noting that the first time you reject a token, the sequence is now different, so you can't continue sampling from the small model. You can't continue that sequence anymore. It's a fun exercise to show that with these sampling probabilities, you have the exact same distribution as the verifier model mathematically. So this process, called speculative decoding, is completely lossless, and it produces crazy speed gains. And what's more is these speed gains get better as the draft model gets even better at matching the verification model. There's a lot more optimizations I haven't talked about, and inference is a huge area of research. If you take anything from this video, it's that questions as simple as make thing fast can be way deeper than you think, and there's always more to explore and to learn.